Okay, so the fact of it is that motion is everywhere. And your eyes pay much more attention to objects that are in motion than objects that are at rest. Okay, so you just are naturally drawn to things in motion. Okay. And now that we're thinking about motion in terms of physics, we need to understand that when an object is in motion, a lot of things are changing. Okay? Most specifically, its position is changing. So as you walk, as you jump, as you do any sort of motion, your position is changing. So it can change lots of different ways, but we're going to just start with really simple changes in motion, things moving forward and backward. And then we're going to move to things moving up and down. And then we're going to look at things that move both forward and up and down and all that kind of stuff. So we're going to kind of take it step by step, but we're going to look at a change in position. So objects can move in lots of different forms of position changes. Straight line motion changes would be examples like just walking, right, or shuffling, or doing anything in a straight line path, right, even throwing something straight up into the air and it comes straight back down. Those are straight line motions. Circular motion is anything that moves kind of in a circular path. Okay, so like it could be a planet that orbits. It could be a merry-go-round, right? You're standing on a merry-go-round that's going in a circle. Any of those things. An arc position change. What am I talking about when I say arc? Kind of make that motion with your finger, your arm. Right? An arc looks like that, kind of a half circle, or it could be really steep and it could come back down. Those are examples of something called projectile motion. Okay, so when you throw a ball or when you kick a ball, those are examples of projectile motion. So they're moving through the air both horizontally and vertically. And then back and forth type motion would be like, it's called a pendulum, but examples of pendulum would be like a swing set, right? In a big clock, you'll see a pendulum swing. Those are examples of back and forth type motion. So we are going to focus specifically on straight line motion for quite a while. Okay? Our motion always relates to a place and a time. So where's our object at? How long did it take to get there? At what speed are they traveling while they're there? All these types of things. So we're always going to have a place and a time, basically, that we're looking at. You don't have to draw this diagram or anything. This is going to seem really simplistic here for a little bit. Okay, but this is how we get started. So very simply, this object or the car in this picture moves from point A to point B. Right? It didn't do anything crazy. It took it a specific amount of time to cover that specific amount of distance, right? And I hope that this seems pretty self-explanatory to you at this point. Okay? It took a certain amount of time to move from point A to point B. That right there was called what we call a motion diagram. Okay, really original name for it. It's used to describe the motion or the movement of an object. And that motion diagram was even more complex than our motion diagrams have to be. Right? We're going to draw diagrams for some of our problems, and they're going to be even much more simplistic than that. Okay? Motion diagrams, by definition, are drawings of intervals of time. And so it tells us where is our object at every second. Okay? Or with every second that passes, where has our object traveled to? And sometimes we have really regular intervals, and sometimes we have irregular intervals. Okay? But here's an example of a motion diagram. Okay, that has a few more intervals on it. So just take a look at it for a minute, see if you could understand what's happening, and then I want to talk about a big picture. Sorry. So what does it appear that this person's doing? Running, right? They appear to be running. And so when we look at a motion diagram, we assume that every one of these dots or every one of these pictures is taken in equal intervals. So that means every second that goes by, a picture is taken. Okay? So as we see this person at the same distance apart every second, that means they're running at a constant rate. They're not speeding up or slowing down. they're running at the same rate or the same speed the whole time. Because with every second that passes, they cover the same amount of distance. Okay, does that make sense? If we saw the person here, and then here after 1 second, and then here after 1 second, that means they're speeding up, right? They're getting faster. So that's what a motion diagram can tell us is the person moving at a constant rate? Are they speeding up? Are they slowing down? All that kind of stuff. Okay? We're going to use coordinate systems or a coordinate system to help us look at motion a little bit more graphically. So does everyone understand what I say when I say coordinate system? I got a coordinate plane with an origin and all that kind of stuff. So when I say pick an origin, that's basically going to be the place at which our motion begins. Okay? So we're going to put the 0 point of our motion where our motion is beginning from. Not 2 seconds in, not at the end of our motion, but where it's beginning from. So it's at this point, both our time and our position, our initial position, are 0. As we start looking at graphing our motion, we're going to start drawing our motion using arrows, and I'm going to give them even a more specific name here in a little bit. But you can indicate how far something has traveled based on the coordinate system and by using an arrow. And I'm going to show you what that looks like here in just a second. Okay? But we're going to start using arrows to diagram our motion. There's two terms here that I want you to be familiar with. First of which is distance, and it's the total amount of length that's been covered. And that seems obvious, right? But the other term we're going to talk about is something called displacement, and that has a totally different definition. And you need to know the difference between these two things, okay? Because we use displacement much more often than we use distance. So distance is the total amount of length, right? It could be in meters, it could be miles, it could be steps, whatever it is, but it's the total amount. Whereas displacement is the difference of your locations. And so the real definition kind of that I want you to think about is this one that's in parentheses. How far you ended up from where you started. Okay, and you might seem to ask like, well, aren't those two the same thing? Okay, but they're really not. Okay, so distance, when we concern ourselves with distance, we care about the path we took to get there. We care about how we got to our final destination. With displacement, we don't. We only care about how far we are from where we started. Okay, how far we are from where we started. So this right here is the equation for finding displacement. Does anyone know what this Greek letter is called?
Delta.
Delta, good. Yeah, delta. And it is a triangle. What does it mean? Anyone know? Difference, oh good, or the change in. Delta means change in. So this is delta, and it means change in. Okay, or you might hear me refer to it a lot as final minus initial. Okay? What'd you say? I would write that down. We'll deal with this delta with a lot of different variables, so we'll see it a lot. You'll get comfortable with it. But for right now, you need to understand it's final minus initial. So as I'm looking at this equation here, for delta displacement, that's what this lowercase d stands for, is displacement. What I'm doing is taking my final displacement minus my initial displacement. So these little subscripts here, F and I, will always stand for final and initial. Okay, and we'll use those subscripts on a lot of different variables. We'll use them with velocity and acceleration and time and all that kind of stuff. Okay, not really time actually. But we're going to use those throughout the whole rest of our year as final and initial subscripts. So pay attention to those, okay? Displacement is what we call a vector quantity. Have anybody heard the term vector before? Okay, it might be pretty new to you. Vector means any measurement that has to have both magnitude and direction. So I want you to tag on the beginning of that definition, it's any measurement that must have both magnitude and direction. So a vector is a type of measurement, and it has to have both magnitude and direction. And so you were probably thinking like, oh, what's magnitude, right? Magnitude is just the size or the number. Okay, so if I told you something was 40 meters east, what is the magnitude part of that measurement? 40 meters, right? So here's the magnitude, and here's the direction. Okay? So this vector quantity has to have both magnitude, which is the number, and the direction. And the direction can be a cardinal direction, what are the 4 cardinal directions?
Northwest.
Good. Northeast. How many of you are just like direction people? Like you know where north is all the time? Did we talk about this before? I'm not that person. Okay, so vectors is a type of measurement, and displacement is an example of a vector. But a scalar, okay, sorry, I already gave you the vector. Vector is representation of motion, or it's a measurement that has to have magnitude and direction. Okay, so we already talked about that. You don't have to put that down again. So an example of a vector would be if I went forward, that can be a direction. Backward can be a direction. The cardinal directions can be directions. Even positives and negatives can indicate direction. So in this class, you'll start to understand that a negative doesn't mean a negative number. A negative tells us that we went south or west. Okay, so the negative will start to indicate to us direction. A scalar is a type of measurement that does not need direction, so it only has a magnitude. Okay, so distance is an example of a scalar. We don't care where we ended up. We just kind of have how far did we go. But we have there's a difference between those two things. Okay, so vectors have to have both magnitude and direction. Scalars don't. Only have a size. Which is what we're going to work with today a little bit. When we draw a vector, which we draw using an arrow, like I said earlier, we need to try to draw them to scale. Okay, and when I say to scale, any idea what that means?
The right shape, or not right, the right size.
About the right size, right? We want them to be proportional to each other. Okay, and so what that means is if I have a vector that says 10 meters, and a vector that's 5 meters, did I draw them to scale? No, right? I didn't have to get out my ruler here, but you can see like if I'm drawing one that's twice as long as the other, I need to draw them twice as long as the other. So when we're drawing our vectors graphically, or when we're showing them graphically, you need to draw them proportional to scale, right? Sometimes I'll ask you to get out a ruler and do it that way, but most of the times I just want you to try to draw them proportionally to scale, okay? So when we draw vectors, and when we're talking about adding vectors, we're going to use what's called the tail to tip method. So what that means is if I walk 10 meters east, then I walk 10 meters north, I add one vector right onto the back of the last one, basically, or to the front of the last one, kind of. Okay, so here's my starting point. There's the origin. I walk 10 meters east, then 10 meters north, right? That's what tail to tip means. I put the tail of my second vector on the tip of my first. Okay, the tail is always at the starting point of our motion. So I said we always start with an origin, right? We pick a 0 point. Let's say I walked west, and then I walked south, and then I walked east a little bit, then I walked north, and then I walked east. Okay, so all of those things are showing the path that I traveled, and I'm adding all those vectors graphically. Okay, does that kind of make sense, tail to tip method? We're always going to start with the tail at the origin, and then we're always going to have the tip that ends up somewhere else, okay? The tip always goes in the direction of the motion, so the arrow itself needs to be drawn in the direction of our motion. That should be pretty self-explanatory. If I'm walking to the east, I need to draw it to the east, okay? Are we good with the fact that this is north, east, south, and west?
Wait.
Okay. On paper, we're always going to assume the top of our paper is north, right? The right of our paper is east. Okay, so no matter what direction you're facing in the classroom, we're always going to assume the top of our paper is north. Are we good with that? I'm not going to ask you to compass yourself to the north. Okay?
We've got
Yeah, no, we're not going to do that. We're just going to assume as we sit, north is to the top. Okay, before we start drawing some, we're going to do some practice here, but I want you to get all that vocab out. Before we draw some, we need to know what happens after I've drawn my whole path of walking, and I want to know how far am I ending up from where I started. I'm going to draw what's called the resultant vector, and that's the sum of all vectors on my diagram. Okay, the graphical sum of all vectors on my diagram is called the resultant vector. So I'm going to draw kind of another example of this here. Here's my coordinate system. You don't have to draw this example, I just want you to kind of follow along. So let's say I walk west, and then south, and then west again, and then I walk north, and I walk east, okay, I'm doing all of this crazy path. Okay? So I had how many total vectors here?
7.
1, 2, 3, 4, 5, 6, 7 vectors, okay? And so let's say I want to find out how far am I from my original starting point. Okay, so I'm going to draw what's called a resultant vector, which goes from the origin to the tip of the last vector. So that green one is my resultant vector, okay? And it's showing me how far am I going to end up from where I started. I don't really care the whole path it took me to get there, but this green one is called my resultant vector. And so we're going to learn how to solve for what's the length of my resultant vector, what distance does that represent, all that kind of stuff. Okay, does that kind of make sense?
So not the length of the path, but the length to
Exactly. The length of the path would be my distance. Exactly. Length of the path would be my distance, but my green, that's my resultant vector, so that would be my displacement. Very good.
Is that the first green dot, the scalar?
No. The green dot is just my starting point. That's my origin. So the resultant vector always goes from the origin to the tip of my last vector.
What's the scalar?
A scalar is just a type of measurement that doesn't need direction, so we won't deal with scalars right now. Okay? Does that make sense? All the red arrows, those would be my distance. If I wanted to add up how many total meters did I walk. But we won't deal with distance very often. We're going to deal with displacement, which is the length of that green arrow. That's what we're going to practice with pretty soon. Okay? So let's look at this example. You can draw it out if you want, but you're also just welcome to just watch, okay? The runner starts at the origin, which is right here, okay? They ran forward 2 meters, so we're going to assume that, they're running horizontally, and forward on our paper would be to the east, right? So they're going to run 2 meters, assuming that all of these are 1 meter apart, okay? So we ran 2 meters. Then we ran backward 6 meters. So from the tip of my last vector, backward would be 1, 2, 3, 4, 5, 6. Would we agree with that? We don't start over at the origin. We go backward 6. Then we go forward 4. 1, 2, 3, 4. Then we go forward 5. 1, 2, 3, 4, 5. Which means that's where we're ending up. So our resultant vector goes from the origin to the tip of our last vector. So what's our final displacement here? 5 meters, what? Yeah, forward or east, right? We said vectors have to have a direction. So you have to include that forward or east on this case. Yeah, Jake?
So wait, why is forward to the...
In this case, we're going to go 11 kilometers north, then 11 kilometers east. So I'm going to assume each of these is 2 kilometers apart. So we'll see where 11 ends up at. So 11 kilometers north means we're going starting at our origin, 2, 4, 6, 8,
It's going to be the very top.
Wait, how are you going to graph that?
10, 11 goes about right there. Okay? There's 11. Now I'm going to go east. So do I start from the origin again?
No.
No, I don't. I start from here. 2, 4, 6, 8, 10, 11, right? Roughly right there. Okay, so if I wanted to draw my resultant vector, I go where?
From the origin to the tip of the last vector.
Good. From the origin to the tip of the last vector. When you guys are doing this yourself, you're going to be super tempted to just draw your 11 kilometer one like this. And then you're going to try to draw your resultant like that. But it doesn't work. Okay, the hypotenuse is the same, but it doesn't give you any indication as to from your starting point where are you ending up, right? Because it's not leading us anywhere. Okay, so let's undo that. We'll go 11 here. So our resultant from the origin to the tip of the last vector. So that purple is our resultant vector. Now if I wanted to find out what's my final displacement, and I know this side's 11, and I know this side's 11, are we putting together the dots here? What am I doing?
A squared plus B squared equals C squared.
Pythagorean theorem. Good. I need to use Pythagorean theorem to find the displacement here. So let's do that. Get out your calculators.
I forgot.
Get out
It's like the 45, 45, 90.
Yeah, this is the right triangle.
Wait, so what? I forgot.
This is a 45, 45, 90 triangle, but
Oh, it equals C squared.
A squared plus B squared equals C squared.
Oh, okay, so that's easy.
Mm-hmm.
Squared. So it's 50.
I got 15 and a half.
You take the square root of that. You gotta take the square root of that.
The square root of 242 is...
Yeah.
What in the...
What did you
You know
get?
what squared
What
add?
does this happen
Look,
to me?
Let me see.
look, a squared plus b squared. You messed up.
I got messed up square now.
Equals c squared.
See, I got that. What
Look,
did you
square
do?
root.
Oh, you squared it. I squared it. Classic. Okay, at least it wasn't like a bad mistake.
Okay, so now we have to include with a vector, we have the size, we have the magnitude, we have to include, what else with a vector?
That'd be like northeast.
Magnitude, yeah, good, northeast, but it's not quite specific enough.
It's
We have to tell at what angle, what angle northeast are we talking about here?
this is another math problem.
Yeah?
Wait, it's 45, 45, 90.
Yeah, this one happens to be 45. So it works out?
Not all of them do.
No. Okay, so 45 degrees. Do you know why, we understand why it's 45 degrees? Both of our sides are the same? Okay, and in this case, since it's 45, we can either say it's north of east, or we can say east of north. That only is applied when it's a 45 degree angle, but I'm going to teach you how do we know if it's north of east or east of north? Is that going way over your head right now?
Yes.
Yeah,
No,
a little bit?
Why
All right, so let's go through a little bit slower.
do we have
If-
to say up?
Because you can't just say northeast, because if it was 10 degrees northeast, we don't know is it 10 degrees northeast this way, or is it 10 degrees northeast this way?
Why does it matter?
Well, because if you start one way, if I'm trying to give directions and I say you need to go 10 degrees from your starting point southeast, and you go to here or you go here, that's going to give you two very different ending points. Right? So we're trying to get the person to our end point. Okay? You can do it. You can do this one. Looking at the one we have drawn right here. Do you think it's east? Do you think it's east of north or north of east? Right here. But looking at the triangle we have drawn.
Probably like,
I know it's in the middle.
I'm gonna say northeast is
East of north.
North of east, you wrote it down first.
It's east of north. Okay, so let's just walk through it. Okay.
Because the yellow
there's not even yellow up
the
there.
purple line, the edge vector is closest to the east. Wait, no.
Is it because we went up first and then over?
Kind of. Okay, so let's listen. When we draw this triangle, it's always going to be a triangle because we're going to use purely north and purely east or whatever it is, okay? So you're looking at what axes does our triangle touch? North or east or south or west? What axes does this triangle touch?
Northeast.
Right here. No, this one right here. This angle. What axes does it touch? The north axis, the east axis, south or west?
The east. I'm
Look,
trying to.
this angle right here, it touches the north axis. Would you agree with that?
Yeah.
Okay? No, touching just this one. Not the purple line. That's not on an axis.
Oh, you mean like the black line?
Yep, an axis. Okay? So it's touching the north axis. Then we decide, does our triangle swing to the east or to the west? Is it east of north or is it west of north? East of north. Okay?
One little thing's going.
Mm-hmm.
We're gonna go downhill. Now we understand it, and then it just gets sad.
All right, so we did a little graphing. We're going to talk more about graphing and adding vectors later. But the reason we're talking about all that stuff is to get to velocity. Velocity is like the quintessential like vocabulary in physics, right? Velocity is change in displacement over change in time. Or another way to say velocity is how fast you're going, right? What's the speed? Speed and velocity are two different things. But essentially, that's what we're looking at. Change in displacement over change in time. So, your first physics equation. Velocity equals distance over time. Okay, change in displacement over change in time. This line means average. Your book puts it in there, but I won't ever write it, so you don't have to put it on there. Okay? Velocity equals change in displacement over change in time. Okay? This is a big day for you, your first physics equation. Okay, so knowing what we know about direction, what do you think a negative velocity is?
Is it time divided by displacement?
No, just means it's going backwards. It's just going backwards. So negative velocity usually indicates that we're going south or west. Okay? South or west are negative directions because on a coordinate system, those are in your negative quadrants. Right? Would you agree with that? That's why negative is going to be labeled south or west. Okay? It could also mean something's falling downward, right? That's kind of considered south. So that's what you're looking at there. Okay, so that's what negative velocity means. You're moving backwards or you're moving in the negative direction. The units for velocity are meters per second or any version of length divided by time. So length per time. We will consistently use meters per second. Okay, which is why we worked on calculating kilometers per hour to meters per second. We're going to want almost everything in meters per second. Okay? Okay, so this tells us a car travels with a velocity of 50 meters per second east for 2 minutes. Then they turn south and travel 30 meters per second for 2 minutes. What was the total distance covered? So they're not asking for displacement here. They're asking for total distance. We want to find how many meters did they drive during this whole time. Okay? We have two different portions of our trip here. So we're going to solve this problem using two different equations. Okay, using two different equations. The first portion of our trip, I'll make here in red. Second portion of our trip, I'll do in purple. Okay? Does it make sense why we have to do this in two different portions? Okay? They're not traveling the same velocity in both of them, and they're traveling in different directions. Okay? So we're going to use that equation I just gave you, velocity equals distance or displacement over time. You'll see me kind of drop that delta off because we're always going to assume that time starts at 0. So if your initial time is 0, there's no use to take final time minus 0. Okay? So you're just always going to have kind of the time it takes. So for the first part, our velocity is 50 meters per second east. What's our time here?
2 minutes.
2 minutes. Can we leave it at 2?
No, 120 seconds.
Good. It has to be in seconds. It needs to match. So if this velocity unit is meters per second, then that means this needs to be in meters, and that means time needs to be in seconds. Right? So our units have to be consistent throughout that equation. So time needs to be in seconds. So to convert minutes to seconds, we multiply by 160, and we get 120 seconds. Are we all on the same page for that? Okay. So now we're going to solve for the distance or displacement. 50 equals change in displacement over change in time, which was 120 seconds. Okay, what do we do to solve for this variable? Mathematically. Multiply each side by 120. Yeah, because we're solving for displacement and that's already in the numerator, so we're going to leave that. Okay, change in displacement equals 6,000 meters. Okay? My initial displacement I'm always going to consider to be just 0, right? Because that's where our motion starts from. So that means we drove during that time 6,000 meters. Are we on the same page there? And we drove that really east. Okay, that's not too important to us right now. Second part of it, we're going to do the exact same thing. We drove 30 meters per second for 2 minutes. That's an S, not a 5. Okay, so to solve for displacement, I'm going to multiply by 120 on both sides. So if I wanted to find the displacement, I would build my triangle and I'd find my resultant. But here, it only wants to know the distance. It wants to know how many total meters did I drive. So what do I need to do to these two values? Just add them together, right? If I wanted to find displacement, I would do my triangle and I'd find my hypotenuse and all that kind of stuff. But here, I just want my distance, so I'm adding them together.
In this case, like, if it would be 9,600 meters per second, would you say east to south or southeast or west?
Well, this is just asking for distance, which doesn't have a direction.
Okay,
So all it is 9,600 meters. That's it. No direction. Because you can't give a direction here because we went south for part of it and east for part of it. Okay? Just total distance, total meters. Okay? Questions there? All right. Sorry, I went backwards. Now I want you to find the displacement. We know how many meters south they traveled and we know how many meters east they traveled. So you're going to draw that diagram yourself. Okay, we went east for 6,000. And then we went south for 3,600. Right, do we know where these numbers are coming from and why I'm drawing the diagram the way I am? Adding them tail to tip. So I need to find the hypotenuse and I need to find that angle. Okay, you're going to use Pythagorean theorem to find that hypotenuse, and then usually we're going to use second tangent to find our angle.
What do you want us to
We want to get there. It's 40 kilometers east, and we need to get there in 32 minutes. If we want to take exactly 32 minutes to get there, what's our velocity have to be? In meters per second. So that means you need to do conversions before you put it into your equation. Okay? Remember our equation, velocity equals displacement over time. Displacement over time. You'll see me drop that delta, right? But final minus initial. When we're starting to read these problems, you need to start picking out your variables as you read them. And I got the hiccups today. 40 kilometers, what type of variable does that tell us it is? It's a displacement or a distance, right? So you would say displacement final is 40 kilometers. Displacement initial is like always 0. Okay, so you don't even really need to include that. That's why you see me drop that delta, because our initial is almost always 0. Okay, so you'll see me just say displacement, but I'll put it up there for now. And right now our time is in minutes. It needs to be seconds. So if we go from minutes to seconds, we multiply by 60. 19, 20 seconds. What do we need to do to this to get it to meters? 1 kilometer equals 1,000 meters, which means it's 40,000 meters. Okay, so now I've got my displacement and I've got my time. How do I solve for velocity?
Divide.
That's it.
And then multiply both by 1.
I got 20.8.
You don't have to do anything except divide meters by seconds. That's it. 20.8.